Hi everybody, we're going to take a look at 4.4, the shape of a graph today. So I just have a warm-up here. We're going to review taking the first two derivatives, then we're going to review sketching a graph given information about the derivative, and then we're going to determine whether a graph has a min or a max, and I'm going to give information on that soon. So the first derivative requires chain rule. Remember that sine squared theta is the same as sine theta squared. Okay. And then the second derivative is going to require product rule. So we have 2 cos squared thetas minus 2 sine squared thetas. Okay, so the second thing is sketch that graph when the derivatives are either negative or positive, and how do we take information from there. So I'm going to put the numbers on here. -2, 2, 3, and 6 are the values that they talked about here, with the derivative being either negative or positive. So from -2 until 2, the derivative is negative, which means that the graph was decreasing. Okay, so it doesn't really matter exactly where I put it, but also I want to keep in mind that if I do go from negative to positive on my derivative graph, that would have also implied a 0 on my derivative graph, and therefore a turning point on my original graph. So I must cross over at -2 and at +2, meaning I have to have maxes or mins there. And same thing at 3 and 6. Right, so I know that I'm negative and therefore decreasing here. I was positive from 2 to 3, and I was negative again from 3 until 6. So it's a matter of increasing or decreasing. So I'll highlight for us to see a little bit better. We are increasing here, here, and here, and decreasing specifically where they said from -2 until 2, and from 3 until 6, because the derivative was negative. So here's the graph that should be given. This is the graph of f prime. Determine where f has a max or a min. All right, so if we're looking for a max or a min from the original function, we have to determine where was that graph increasing or decreasing. And that shift, that transition, is where the mins and the maxes would occur. So if a derivative graph changes from positive to negative, that meant that a original function changed from increasing to decreasing, and therefore would have a maximum. So we're going to have a maximum at C. And if a graph changes from decreasing to increasing, then we're going to have a minimum. So, or a negative to a positive. So we're going to have a minimum at A and E. Okay, so the second derivative is going to bring us to this conversation of concavity. And that's what this section is all about. So concavity refers to the way the graph bends. There are two types: concave up, includes the minimum; concave down, and that includes the maximum. Concavity is dependent on how the slopes of the tangent lines to the original graph are changing. If the slopes are increasing on an interval, then the graph will be concave up. If the slopes are decreasing on an interval, then the graph will be concave down. If a function changes from concave up to concave down or vice versa at a point, then that point is an inflection point. What function will we use to describe the rate at which the slopes are changing? So we're going to use the second derivative. The rate at which the slopes are changing, the rate of change. So theorem 1, test for concavity. Assume that f double prime exists for all x belonging to a to b. If f double prime is positive, then f is concave up on AB. If f double prime is negative, then f is concave down. We can use a process similar to interval testing with critical points to determine the inflection points and the intervals on which the function is concave up or concave down. Okay, so here's our first example. Find the intervals on f, on which f is concave up and concave down, and find the points of inflection. Okay, so we have first derivative, second derivative. Just like before, we want to be in factored form. Here we're going to get two possible points of inflection, 0 and 1. Okay. We're going to interval test around those values to see if we have change in concavity. So we're going to go from negative infinity, because this is a polynomial, until 0, 0 until 1, and 1 until positive infinity. Okay. So if we pick any negative value, negative 5 is in my head, then I would have a positive 60 times negative 5 squared, and then a negative 5 minus a 1 would be a negative. So this is negative, and therefore concave down. If I use a value like 1/2, positive for 60x squared, but negative for x minus 1. So still negative, still concave down. And then if I pick any positive value, like 5, we would have positive, positive, resulting in concave up. So because we have a change from down to up, we have a point of inflection at x equals 1 only. This is what the graph of that function looks like. So you can see that, yes, something at 0 is going on, but there must be some sort of an imaginary solution in that area. Therefore, we're not having true turning points or points of inflection at that moment. But at 1, we can see that's where the graph changes from facing downward to upward. That's where that transition happens. So theta plus sine squared theta. So this was what the warm-up was. Remember, we did first and second derivative already. So 1 plus 2 sine theta cosine theta. And then it ended up being 2 cos squared theta minus 2 sine squared theta in the warm-up. So we want to factor this, set it equal to 0. Domain is 0 to pi, that's helpful. So I can, if I set equal to 0, I can divide out that 2, it doesn't matter. And I'm going to factor this like a difference of squares. Cos theta plus sine theta times cos theta minus sine theta. So we solve each of these. When is cos theta equal to negative sine theta? And when is cos theta equal to sine theta? So this is at the pi over 4s, right? The negatives happen at 3 pi over 4. And the same sign happens at pi over 4. So we go from 0 until pi over 4 until 3 pi over 4, and 3 pi over 4 until pi. So in the first quadrant there, 0 to pi over 4, I can use my pi over 6 angle 30 degrees to figure out if this is going to be a positive or a negative. Because of the way it's squared, you can use cosine squared theta minus sine squared theta to think about the sign of this. That's fine. So 30-degree angle, my x-coordinate is larger, my cosine is larger than my y, or my sine in that place. So that's going to make cosine squared theta minus sine squared theta positive and concave up. But as we move around the unit circle, and we go here to now pi over 3, the x is smaller. We have a 1/2 comma root 3 over 2. So now it's going to go negative. And then when we move back over to here, it would be the same logic that the pi over 6 in the second quadrant, the 5 pi over 6, the x is larger than the y, and since they're both squared, it doesn't matter that one is positive and one is negative. So it's positive and concave up. So because we have changes, then we have 2 points of inflection at both pi over 4 and 3 pi over 4. Okay, to summarize here, currently to find the local min or max of a function, we must find the critical points and perform interval testing using the first derivative. Sometimes we can use the second derivative test to save us time. If the second derivative is positive, then the graph is concave up. If a function is concave up on an interval and has a critical point in the interval, then the critical point must be a local minimum. And if a function is concave down on an interval and has a critical point in the interval, then the critical point must be a local maximum. So this test can be helpful. I've found over the years that I use it more as a check, just to confirm that along the way that everything matches up. But you can use it for this reason alone. Okay, so the second derivative test states that if f double prime of c is greater than 0, then f of c is a local minimum, as long as c is a critical point, of course. And then if f double prime of c is negative, then f of c is a local maximum. And if f double prime of c is 0, it's inconclusive. It still might be a min or a max. Okay, so let's try this. Analyze the critical points of f of x equals 2x minus x squared quantity times e to the x. So first find the critical points. So we need our first derivative. So product rule here, we would have 2 minus 2x e to the x. I'm going to factor out the e to the x. If plus and minus root 2 e to the x never equals 0, then we can apply the second derivative test. So if we derive the first derivative, and I'm going to note that my first derivative did simplify to e to the x times 2 minus x squared, and that's where I'm going to derive from. So using product rule, I get here. Again, I'm looking to factor this out. I'm going to pull out a negative. Okay. So this is the simplest form of my second derivative, and all I'm doing here, I'm not continuing with interval testing and such. I just want to know, is my second derivative positive or negative at those critical point locations? So I want to know, well, at f root 2, what's it going to come out as? So the negative e to the x, well, that will yield a negative factor. And then the x squared plus 2x minus 2. So root 2 squared would be 2, plus 2 root 2, minus the 2. Well, I'm going to end up with that 2 root 2, so this is going to be a positive. So this is negative, concave down, and therefore positive root 2 must be a maximum. And if I do this with negative root 2, negative e to the negative root 2, that's still negative. And then negative root 2 plugged in there, I would have negative root 2 squared, which would be 2. So the 2 minus 2 constant cancels, and then I would be left with that middle term of 2 times negative root 2, so a negative. So overall positive, concave up, and a minimum. Right, because it's down here versus up there. Okay. I'm going to leave this one for you all to try, and we can go through it together in class.